Hi, today we are going to look at ODEs, and in this video I don't want to solve a whole lot of questions. All I want to do is to convey the whole idea of ODEs and be able to place it side by side with all of its related concepts in calculus, so that you get the big picture idea of what ODEs is before we can go on to the specifics of what an ODE is. So the first thing you have to know before you know ODEs is, first of all, what is an equation, okay? And for that matter, what is a function, okay? Because the functions in this case, the equations in this case will involve functions. And you also need to know what is the differential part of the ordinary differential equations. So we start with a function. A function is a mathematical machine, okay? And I say machine loosely to say it's something that transforms something into another thing. That when you put some independent variables or variable inside of it, you get a dependent variable out of it. So for example, you have this as a statement of a function. The y represents the dependent variable and the x represents the independent variable. So you know this from way back, but it is very useful to introduce it to ease the pain of thinking about these as separated concepts. Okay. An equation is a mathematical statement with an equal sign. That is the most basic statement of what an equation is. So here there's an equal sign, so this is an equation. Here there's also an equal sign, so this is an equation. So basically that's an equation, okay? Now, differentiation is the process of finding the rate of change of a function with respect to the independent variable. So you see, differentiation has built on top of what a function is. So you have a function, you want to know what happens to the whole function itself if the independent variable changes by a little amount. You use the tool of differentiation. Now, if you do that and you want to undo what you did in differentiation, you use a concept called the integration, okay? But integration involves a lot of guessing. The function is not always known. You can't use a brute force method like you do in differentiation. You can always try to be like, okay, let me use tricks, let me do this, and you finally get to the answer. There are so many rules. There are different rules for differentiation. Yeah, don't get me wrong. There are also rules for integration. But integration is much more harder because most of the time you just have to admit it and use numerical methods because you don't know what the integral of something looks like. For example, there are some mathematical concepts of elliptic integrals that are very notoriously difficult to integrate. So they use computer simulations only to get the numerical values for real-world computations. For example, in the simple pendulums case, when the angle is not close to zero or not approximately zero, the integrals are quite complicated. So yeah, that was just an example. But now that we understood our goal here, I want to relate it naturally to what ODEs are. Okay, when we think about differentiation, what comes to our mind is this. You have a function equal to, let's say, 5x squared plus 2, okay? And you try to differentiate this. And you know how to do differentiation in Calc 1. So the concepts from Calc 1 are brought here, but we are still reversing the whole thing, okay? So this is in differentiation. You get 10x plus 0 because the differential of a constant is 0. Now that you have this, if they ask you to reverse it back to this point, you know how to do it. If they ask you to reverse it back to the original function, you know how to easily do it. You could say, okay, y prime is the same as dy dx, and this is equal to this. So I can then do this 10x dx and integrate both sides to get back my y to be the integral of this is 5x squared plus 2. But you don't know, okay? At this point you have lost the constant, so in order to take care of the constant, you just say, okay, I assume there might have been a constant that I lost in the process of differentiation. So that is the whole goal of integration, okay? So moving from here, the 10x back to here was not that difficult, okay? But the next natural question is, what if you have the whole thing like this, y prime equal to something like xy? What will you do? How will you just do the integration straightforward? Okay, even a more bizarre case is, what if you have something like y prime equal to y squared x or something? How are you going to do it? Because this doesn't look right. It doesn't look like this normal form that you can go straight forward and do. That is where differential equation comes in. Differential equation gives us a whole toolbox to be able to transform the bizarre cases, something like this or something like that, into a form that is integrable so that we can find y. Our whole goal in differential equations is to transform an equation into a form that is integrable. Good. But let me rewrite this and we will demonstrate the parts that represents the differential and the parts that represents the equation. Okay, so let me rewrite it. Y prime equal to xy. Now, why do we call it a differential? Because there is a differential inside, okay? And why do we call it an equation? Because there is an equal sign inside, and the equal sign qualifies a mathematical statement as an equation. So that was it about differential equations. The last thing we would note about ODEs is that the O in ODEs is ordinary. What is ordinary about it? The ordinary about this is that we are using ordinary differential equations instead of partial differential equations. There is a distinction between all of those, okay? The distinction is that in ordinary differential equations, you only deal with the rate of change with respect to one specific variable, or you deal with single variable functions. You don't deal with multiple variable functions. So in the machine, you just put one variable. But in in partial differentiation, you have to deal with the change when there are so many variables. So that's why we have partial differentiation. So just as ODEs, in other words, ordinary differential equations, provide tools and tricks to integration so that it can reverse ordinary differentiation, partial differential equations or PDEs also provides integration with tools and tricks so that it can reverse partial differentiation. So that's the whole deal. The whole drill is, well, when they say types of them, PDE came about because we had a desire to reverse partial differentiations, and ODEs came about because we had a desire to reverse ordinary differential equations. So that is it. I mean, this chart was drawn to show you that, I mean, this whole thing is still part of calculus, okay? We had Calc 1, we had Calc 2, we have multivariable calculus here, over here, and so many others. We have multivariable calculus, we have integration, we have differentiation, which consists of ordinary differential equations, ordinary differentiation and partial differentiation. We have ODEs, which is ordinary differential equations, which we are doing now, and we have PDEs, which is partial differential equations, which we'll do later, and we have differential equations. Differential equations is actually these two, and some other crazy stuff, crazy branches of calculus like fractional calculus and vector calculus. So this is an overview of what OD is in terms of the scope, okay? And you already know what a dependent and independent variable is, and you know what ordinary and partial differentiation is, and why ODEs exist to reverse differentiation and so on. So thank you very much for watching, and I'll see you next time when we come back to talk about what ODEs are and how to solve them.